Guys, in this video we're going to be going through indices and index laws. So I'm sure everyone's seen index notation before, but let's go through the basics again. So in index notation you have two components. You have the base, or the big number at the bottom, so that can be either a variable or a number, and then you have the index, which is the small number in the corner. And what the index tells us is how many times the base has to be multiplied by itself. So if we have a squared, that means we have a multiplied by itself twice. So a times a. If we have a cubed, that's a times by itself 3 times. And if we have a to the power of 4, that's a times by itself 4 times, and so on and so forth. Looking at a few examples, here we have 5 and 1, 2, 3, 4 m's. So to simplify that into something with index notation, we would simply write 5m to the power of 4. Keep in mind the 5 does not have an index since we only have one 5. Looking at the second one, we have 1, 2, 3 a's and 2 b's. So we write 7a cubed b squared as our answer. Finally, for this one, we have 5 10s, so we just write 10 to the power of 5. So that's pretty simple. In this question, it asks us to expand these indices into an expression without indices. So looking at this expression here, we can see that there's a 5 and a p squared and a q cubed. So the p squared tells us that the p is multiplied by itself twice, and the q cubed tells us the q is multiplied by itself 3 times. So we write 5 times p times q times q times q. So that's the unsimplified version of this expression. Moving on to multiplying using index laws. So if two expressions with indices have the same base and we multiply them together, then we would just add the indices together. So if we were to multiply a cubed by 4 cubed, we would get a to the power of 7. That's pretty simple, but you just have to make sure that the base of your expressions are the same, otherwise you can't do this. So moving on to this example, this is really similar to what I just explained. So if you have two expressions with the same base and you multiply them together, then the indices just add up. So you get a to the power of 6 plus 8, which is a to the power of 14. Now, why did this work? Well, a to the power of 6 is just a times a times a, blah, 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 6 times. And a to the power of 8 is just a times a, 8 times. So if you multiply these two together, that's just a multiplied by itself 14 times, which is the same as a to the power of 14, and that's why this works. Moving on to this example, as you can see here, they've multiplied 3 different expressions with indices together, and they all have a base of x. So since they all have a base of x, we can add the indices together, giving us x to the power of 12. Also keep in mind that the numbers on the outside are just multiplied together regularly, giving us 24x to the power of 12. And keep in mind that these numbers don't have indices as well, so they just multiply like normal. Moving on to dividing in algebra, so just like how multiplying, when we multiply expressions with the same base, we just add our indices together. When we're dividing two expressions with the same base, we just minus our indices. So very similar to multiplying, but the opposite. So looking at this example, we've got a to the power of 12 divided by a to the power of 4. So all we do is we take away the 4 from the 12, giving us a to the power of 8. Looking at this example, they've done the same thing again, so just m to the power of 6 minus 2, which is m to the power of 4. And with our numbers on the left side, which don't have a power, they just divide like normal. So 12 divided by 4 is just 3. So we have a 3 on the left side of our answer. Next, moving on to power of indices. So this is somewhere where a lot of people will make mistakes because they've been told when they multiply indices together, you add them. So a lot of people will write a to the power of 5 as the answer to something like this, but that's not actually true because the a to the power of 2 is our base and our index is our 3. So what that means is we have to multiply a squared by itself 3 different times. So that's a squared times a squared times a squared, which is the same as a to the power of 6. So when we're working with brackets, we actually multiply our indexes together. Looking at this example, we have a cubed to the power of 5. So we just multiply the 3 and the 5 together, giving us a to the power of 15. Looking at this example, as you can see, they've multiplied the 3 and the 2 together, giving us m to the power of 6. But what they've also done is they've squared the 4. So we have 4 to the power of 2 as well, giving us a final answer of 16m to the power of 6. So one thing you have to keep in mind when using brackets is that the power on the outside of the brackets has to apply to every element on the inside of the bracket. So the 4 and the m both have to be squared. So that's a really important thing to keep in mind. Make sure you don't forget this. Finally, moving on to things to the power of 0. So this is actually really simple. There's just one main thing you have to remember, and that's anything to the power of 0 will always equal 1, no matter what it is. So you could have like negative 99,999 to the power of 0, and that'll equal 1. So it doesn't matter what number it is, anything to the power of 0 is 1. So looking at some examples, this one, 7 to the power of 0, that's just equal to 1. 5x to the power of 0 plus 7, that's the same as 5 times 1 plus 7, so that just equals 12. This one, 3m to the power of 0, that just equals 1. And yeah, that's about it for things to the power of 0. And that's the last bit we're going to be going through in this video. So we're going to be going through scientific notation. So before we begin, what is scientific notation? Well, scientific notation is just a way that we can represent numbers which make really large or really small numbers in particular, and it just makes it easier for us to see how, what those numbers are and what those numbers represent. Because if we have a really large number, like let's say we have like 9 billion, it can often be really hard to determine how large that number is because it's really hard to see how many zeros or how many trailing numbers there are in that number. So instead of writing 9 billion like this, we would write 9 times 10 to the power of 9. So that just makes it a lot simpler for us to see what that number is, and it doesn't take up as much space either. Scientific notation is also really easy to learn. So basically, if we have something like 7.24 times 10 to the power of 6, What that means is we have to move the decimal space 6 places down. So originally they had the decimal place there, so we move it 1, 2, 3, 4, 5, 6 places down. So the decimal place goes here now. So we get the number 7,240,000. So in the same way, if we want to convert 7,240,000 into a scientific notation, we would move the decimal place one spot after our first digit, and we count how many digits are between here and the end of the number. So between here and the end of the number, we have 1, 2, 3, 4, 5, 6. So we have 6 digits in between, right after our first digit and the end of our number. So we would write 7.24 times 10 to the power of 6. So looking at another example, here we have 691,000 as our number. So we go to the spot right after our first digit and we count how many digits are between here and the end of our number. So 1, 2, 3, 4, 5. There's 5 digits, right? So all we write is 6.91 times 10 to the power of 5. And the same way, in a very similar way, we can convert our scientific notation to a regular number. So we just move our dot here over 5 digits, which gives us 691,000 as a regular number. Now, usually you can calculate scientific notations and convert between scientific notation and regular numbers on a calculator, but that'll be different depending on which calculator you have. But generally, if you are able to use these buttons on the calculator, that'll be able to convert between scientific and regular notation. So please have a look at this and try it out in your own time. Next, we're going to look at scientific notations for really small numbers. So here, we've looked at scientific notations for really large numbers, but we can also use scientific notation to represent really small numbers. So to convert a number such as this into scientific notations, we count how many trailing zeros there are in front of our first non-zero digit. So here, leading zeros, not trailing zeros, apologies. So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 leading zeros before our first non-zero digit. So what does that mean? That means we'll write 9.57 times 10 to the power of negative 8 as our answer. The same thing for when we're converting from. Now moving on to scientific notations with small numbers. So just as with really large numbers up here, we convert really small numbers into scientific notations in a very similar way. So what we do is, again, we want to put a decimal place right after our first non-zero digit. So that's right after our 9 here. And we count how many digits are between this decimal place here and this decimal place we just put in here. So we count how many digits there are. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 digits between this decimal place and this one. So in our scientific notation, we write 9.57 times 10 to the power of negative 8. Negative 8 this time. So what does 10 to the power of negative 8 actually mean? Well, when you have a negative number as your index, you just write it as a fraction. So 10 to the power of negative 8 is equal to 10 to the power of 8 at the bottom of a fraction. So 1 over 10 to the power of 8. So that's the same with any index. If we would write 1 to the power of negative x, that's the same as 1 to the power of 10 to the x. Okay, so now converting from scientific notation to a regular number. Just as with before, if we have a 4 in our index, then we'll have to move our decimal place 4 times, or move it over by 4 digits. But instead of moving it to the right like before, we want to move our decimal place to the left. So we'll move it 4 digits to the left, which will give us this number. Another way to check that we've done this correctly is if we have a -4 as our index, that means we'll have 4 leading zeros before our first non-zero digit. So that's a good way to check if you've done your scientific notation correctly, is that the number of leading zeros is going to be equal to the number in your index. Now again, you're able to convert from scientific notations to regular notations using your calculator and vice versa. So make sure you check that out and try that on your calculator in your own time.